Okay, so here we've got a first question from the International June 2015 M2 paper. Being the first question, it shouldn't trouble us too much, but we need to take care. It's all about impulse, because we've got this bit of information here, and we've got an initial velocity. We clearly need to work out the final velocity in order to work out the kinetic energy of the particle. The changing kinetic energy of the particle. So let's look at impulse. Impulse is changing momentum. Nice convenient way of writing it is like that, which means the same thing. That mass times by changing velocity is clearly going to be the same as changing momentum. It's important we have these the correct way around, because the sign of this impulse, being a vector quantity, is important, and it could go badly wrong if we don't take care with those things. Okay, now, so let's just slot what we need to know so we can work out our velocity, our final velocity here. Okay, that's basically what we need to know in order to work out the change in kinetic energy. Okay, so we have impulse, which is this here, minus 3i plus 3j, equals to mass, which is 0.3, v, which is what we're trying to find out, take away the initial velocity, which we've given here. Remember, it's taking away the whole of that, so we need to not be too careless here either. Right, now, obviously it's not going to be difficult to work out v here, so it occurs to me that in this case it'd be easy to divide by 0.3. So we'll have minus 10i plus 10j. Got rid of our 0.3 nicely without multiplying it through. We do need to be careful with signs again, as I said, for the initial velocity. And so there we have the final velocity is equal to minus 5i. The minus 10i take away the minus 5 plus the 5i, and the 10j plus the 3j there, so that's 13j. Okay, so now we've got the final velocity, we can work out the change in kinetic energy. Delta Ke equals to half mv squared minus half mu squared. Now, because it's only one mass involved, it might be just as easy to write it like this again. What you might be tempted to do is to look at this here and change and work out the magnitude of it, because obviously the velocity, the kinetic energy is a vector quantity, and you might be thinking, well, I need the speed, which would be okay, but in fact we could use the components of the velocity here without having to work out the speed directly, because effectively if you work out the speed, what you're going to end up doing when you work out the v squared is undoing the square root sign, so there's not really any need to square root it just to square it again. So we can look at the individual components here. So we've got that's equal to, let's go back to my original same colour, that's equal to half m, so that's half of 0.3 times v squared. As I say, we can look at our components here, 5 squared plus 13 squared. I don't bother with them. When we're looking at magnitudes, I don't bother considering the minus. It's obviously going to be minus 5 squared. We don't need to worry ourselves, trouble ourselves in pointing that out, so long as we know what we're doing. And then we've got the final velocity, that's the initial velocity. That was the final velocity, and the initial velocity is this, 5 squared plus 3 squared. Okay. well, the 2.5 squared square, so it's half times 0.3, 0.15. And then it's 13 squared, take away 3 squared. Okay, now it's obviously okay to use a calculator here, but as soon as I can see this in front of me, I can't help just leaving the calculator stuff till afterwards and using a difference of 2 squares for this. That's the same as 0.5 times by 10 times by 16. Sorry, I'm old school, so I can sometimes it just feels nicer to do these things by hand, still not use a calculator. Most of you probably worked it out by now, but anyway, 0.5 times 10 is 1.5 times 16, then that equals to 24 joules, and that is it. 24 joules is the answer, and that's our change in kinetic energy. Okay, thank you very much.